It was the largest steam locomotive ever to move under its own power, a machine built to solve a crisis and strong enough to reshape an entire railroad. The Union Pacific Big Boy was not designed for comfort or forgiveness. It was designed to win a race against mountains, time, and war. Its reputation has grown into legend, but behind the size and spectacle lies a far more serious question about risk, danger, and the real cost of harnessing power on this scale. The Union Pacific Big Boy stood apart even among giants, a locomotive so massive that its weight exceeded that of a modern passenger jet, and its strength rewrote assumptions about what steam power could achieve. It was engineered to move freight trains that previously demanded multiple locomotives, dragging thousands of tons across grades that had long punished crews and equipment alike. Yet that capability came with relentless physical demands, extreme operating conditions, and risks that never faded once the throttle was opened. Understanding how dangerous the Big Boy truly was requires tracing the pressure that created it and the environment that shaped its service. The problem began in the mountains of northern Utah, where geography dictated operations. The Wasatch Mountains formed a steep barrier on Union Pacific's main transcontinental line, with a sustained 1.14% grade between Ogden and Green River that turned every heavy train into a logistical puzzle. By the late 1930s, freight volumes had increased beyond what existing locomotives could handle efficiently. Trains approaching the grade often stalled at its base, while helper engines were added, then slowed again near the summit to remove those helpers before descending. Each maneuver consumed time, track space, and manpower, and when traffic peaked, the delays cascaded outward. As global conflict intensified, those inefficiencies became unacceptable. Freight traffic surged as factories ran harder and military supply chains stretched across the continent. By 1942, more than 3 million tons of freight crossed the Wasatch annually, nearly double the volume of 5 years earlier. Union Pacific's own data recorded ton miles on that stretch, climbing from 610 million in 1938 to more than 1.1 billion by 1943. The railroad faced a growing risk that congestion would slow the movement of war materials when speed had become a strategic necessity. The bottleneck could no longer be managed, it had to be eliminated. Union Pacific's planners reached a blunt conclusion. The solution would not come from more locomotives or better scheduling, but from a single engine capable of doing the work of several. That engine would need to pull more than 3,600 tons up a mountain grade without assistance, while maintaining speeds that kept freight moving on time. No steam locomotive had ever been asked to do that before, and meeting the requirement forced designers to abandon conventional limits. At the American Locomotive Company, Otto Jabelmann and his engineering team were tasked with turning that demand into reality. The design they pursued focused on traction, flexibility, and sheer thermal output. The resulting 4884 wheel arrangement placed 2 articulated sets of 8 driving wheels beneath the boiler, allowing the locomotive to bend through curves while keeping enormous weight pressed firmly onto the rails. Leading wheels stabilized the front at speed, while trailing wheels supported a firebox of unprecedented size. That firebox defined the machine. Nearly 10 feet wide, it fed a boiler operating at 300 pounds per square inch, a pressure level that pushed steel construction to its practical limits. Inside, coal burned at a furious rate, converting heat into motion through pistons and rods that delivered more than 6,000 horsepower. Achieving that safely required thick steel plates, thousands of stay bolts, and precise welding capable of containing sustained internal stress without failure. Nothing about the design allowed for casual margins. Weight management proved just as critical. With more than 1 million pounds resting on the rails, uneven track could quickly compromise traction, or damaged components. To counter that risk, engineers adopted a three-point suspension system that distributed mass evenly along the locomotive's length, ensuring that driving wheels remained engaged even when conditions were less than ideal. Surviving drawings from the era reveal calculations focused obsessively on balance and stress, reflecting the awareness that any oversight could turn strength into liability. When the first completed locomotive rolled out of the Schenectady Works in 1941, its scale immediately set it apart. According to railroad tradition, a shop worker scrawled the words "Big Boy" across the smokebox in chalk, and the name followed all 25 locomotives that would eventually be built. Between 1941 and 1944, Union Pacific accepted delivery of the class, each stretching more than 132 feet and weighing over 1.2 million pounds with its tender. Each locomotive cost between $265,000 and $319,000, a wartime investment equivalent to roughly $5 million today, justified by urgency rather than extravagance. Once assigned to the Ogden to Green River route, the big boys immediately altered operations. Helper engines disappeared from schedules, congestion eased, and freight moved through the Wasatch with a consistency previously impossible. Test data confirmed what crews soon witnessed firsthand. Dynamometer measurements showed sustained drawbar output of 6,290 horsepower, allowing a single locomotive to haul 4,450 tons up the grade while maintaining speeds above 40 miles per hour. On level track, starting trains more than 5 miles long from rest became routine. With tractive effort reaching 135,000 pounds, the big boy eclipsed every other steam locomotive placed into regular service. Power of that magnitude demanded fuel on an equally extreme scale. At maximum output, a big boy consumed roughly 11 tons of coal per hour. The tender carried 56,000 pounds of coal and 25,000 gallons of water. Yet sustained mountain operation could drain both supplies in under 3 hours. Managing consumption became a continuous calculation, rather than an afterthought. Every decision in the cab affected range, pressure, and safety. Conditions inside the cab reflected the strain placed on the machine. Heat radiated constantly from the boiler and firebox, pushing temperatures past 120 degrees, even when outside air remained cool. Crews worked soaked in sweat, eyes fixed on gauges that left little room for delay. Steam pressure, water level, speed, and grade all demanded attention at once. An overheated bearing could escalate from warning to failure within minutes, turning a routine climb into an emergency. The locomotive rewarded precision and punished inattention. The danger was real, not symbolic. On April 27, 1953, Big Boy number 405 derailed near Wamsutter, Wyoming, while traveling close to 50 miles per hour. A switch had been set incorrectly for a siding, and the locomotive struck it at speed. The result was catastrophic. The engine and 18 cars left the rails, scattering wreckage across the landscape. Engineer Leo Murray and fireman Lawrence Andres were killed instantly. Brakeman James Anderson survived the initial crash, but suffered severe burns and died 2 days later. Investigators later attributed the accident to a misaligned switch and failures in communication, underscoring how a single error could overwhelm even the most powerful machine. Preventing such failures required constant effort. Each big boy contained hundreds of lubrication points that crews inspected daily using detailed charts. Mechanics worked beneath boilers, checking bearings for signs of overheating, knowing that unnoticed wear could have severe consequences on the main line. Boiler tubes and stay bolts endured relentless stress and required frequent replacement, often in cramped, dangerously hot environments. Heavy cranes were necessary to lift massive driver sets and rods that weighed several tons. Maintenance was not periodic, but continuous, a daily struggle against heat, vibration, and metal fatigue. Despite their success, the big boys emerged at the end of the steam era rather than its beginning. Diesel-electric locomotives arrived with advantages that reshaped railroad economics almost immediately. A 3-unit diesel consist could move similar tonnage with fewer crew members and a fraction of the maintenance hours. Union Pacific's internal comparisons showed cost per ton-mile falling from nearly 7 cents with steam to just over 2 cents with diesel power. Diesels could be started without hours of preparation, operated in flexible combinations, and run for extended periods without intensive servicing. The financial logic was decisive. By the early 1960s, the big boys were withdrawn from service. 17 were scrapped, their steel recycled into a changing industry. 8 survived, preserved across the country as static reminders of a different engineering philosophy. One survivor would eventually move again. In 2012, Union Pacific announced plans to restore Big Boy 4014. After its relocation to Cheyenne in 2013, a dedicated team led by Ed Dickens undertook a meticulous rebuild, costing more than $4 million. The locomotive was converted from coal to oil. Modern systems were integrated, and years of dormant machinery were brought back into working order. On May 1st, 2019, 4014 returned to steam. Positive train control was added in 2021 and introduced 2023. The locomotive assisted a stalled freight, demonstrating that its power remained relevant. Plans for a nationwide tour in 2026 promised to introduce new audiences to its presence. Between 1941 and 1944, Union Pacific placed 25 big boy locomotives into service, each one engineered for a single purpose, defeating the relentless 1.14% climb of the Wasatch Mountains without help. Their ability to haul more than 4,400 tons while producing 6,290 horsepower proved that one locomotive could shoulder the demands of a nation at war, even as crews worked inside punishing heat and under constant mechanical strain. The 1953 derailment near Wamsutter remains the only fatal accident tied to the class, a sobering reminder that breakthroughs in engineering were never separated from human consequence. By 1962, most big boys had been cut up, leaving only 8 behind as physical proof of their scale and ambition. Much about the daily dangers crews faced has faded with time as records are incomplete and first-hand accounts grow quieter. Today, Big Boy 4014 operates with modern safety systems, standing as a living connection between past and present. So how dangerous was the Big Boy on an average day, beyond the numbers and the legends? How many close calls went unrecorded, and how much risk did crews quietly accept to keep freight moving on time? If stories like this matter, and if the hidden costs behind history's greatest machines deserve more attention, make sure to subscribe, because there is much more to uncover.